In this video, we are going to begin talking about path independence, and we're going to build towards learning about conservative fields as well as also potential functions. So far, we've been talking a lot about vector fields. Okay, so this F with the vector bar above it represents a vector field. And when we start talking about gravitational fields or electrical fields, these type of fields, we need to consider path independence. When we think about a gravitational field, gravitational force on a body of mass can create a vector field, same as with an electric field. So some charge can be acted on by an electric field, which would also create a vector force field. In both of these types of fields, the work to move a mass or that charge Q depends on both the initial and the final or terminal positions, not the path. And since the path doesn't matter so much, that means we can be traveling from some point A initial to a terminal point B, and we have lots of different paths that we could take to get there. Okay, so this brings us to the study of vector fields with this independence of path property. So what is path independence? What does it mean? Let's first look at a definition here. So defining path independence, we'll say let F be a vector force field defined on some open region D in space. Suppose that any 2 points A and B in D, the line integral along that path C, and we could have different paths from A to B in, again, my region D, is the same over all of the paths. So that means that my calculation, my line integral, if it's the same regardless of the path, we say that it is path independent in D. And if it is path independent, then the force field is conservative in that region. The word conservative that we see here when we discuss path independence, that comes from physics, and this refers to fields where the principle of energy conservation holds. Talking more about what that word conservative means, we can define a vector field F to be conservative in some region if it is the gradient field for some function f which lies in that region. By saying this, or defining it this way, basically I'm saying is that this force field can be conservative if it's equal to the gradient field of f. So we're going to bring in another word here. So we're saying this could be conservative, and little f here is a potential function. So also defining a potential function here, if this property exists, we have some vector field defined on the region D, and that vector field is equal to the gradient field, then little f is called the potential function. Okay, so we've got some different words we've talked about: potential function, conservative, and path independence. And just refreshing, path independence, what that says is if I can find the line integral over any of these paths and they're all the same, from an initial A to a terminal B, we say that that integral is path independent. Let's look at a little bit more. I'm going to do a small example to kind of help us understand what it means to be conservative and have a potential function. Here we're given a vector field, which is 2xi plus yj. And I'm asking you, is this conservative? And if it is conservative, then it must have a potential function. So by definition, if this is conservative, there exists some gradient of little f for this vector force field. So essentially what I'm saying, is there some function that I can take the partial of with respect to x to get 2x? And is there some function that I can take the partial of with respect to y and get y? Now this could be kind of tricky for us to do because there are a lot of different functions. We're just looking for, in a sense, a potential function. So for example, we could say little f might equal x squared, because the partial of x squared with respect to x is going to give us 2x. And then a y term, 1/2 y squared. The partial of this function, the whole function, with respect to y is going to give us y. So I've got an x term and a y term here. And because this works for both x and y, and this checks, I could take my partials here and I would get that force field. Then we can say f is conservative. And so I know I've jumped around a little bit here, but let's go back and talk a tiny bit about independence of path before we get to our next video, where we'll really define this fundamental theorem of line integrals. As we talk a little bit more about independence of path, what we want to recall is that when we calculated a line integral along some path c sub 1 of f dot dr, that was not equal to a different line integral over path c sub 2 f dot dr, even if they had the same starting and ending points. So what we have been learning so far is that the value of the line integral is dependent on the path. It depends on the path you take from point A to point B. So if we had gone this way versus some other path, that line integral would be different. But what the fundamental theorem of line integrals, which is where we are going, what that implies is that the line integral over c sub 1 of gradient of f dot dr will actually equal the line integral over a different path, c sub 2 gradient of f dot dr, as long as c sub 1 and c sub 2 have the same endpoints. So this is just a little bit different. And this is going to be true for any line integral of a conservative vector field. So as long as the vector field we are dealing with is conservative, which means that, as we said, f equals some gradient of little f, as long as it's conservative, then the path doesn't matter. We have this independence of path, and we can calculate the line integrals as long as the initial and terminal points are the same, the line integral will be the same. So that's what we're building towards, talking about this fundamental theorem of line integrals. So in this video, we talked about path independence, we talked about what it means to be a conservative vector field, and then also to have a potential function.